So, we started multi-electron atom if atom is having more than one electron. So, actually most of the all atoms are having more than one electron except hydrogen atom and other ionized atom, helium plus 1, lithium plus 2, okay, means additional atoms electrons are taken out. So, that is the single electron system that we have studied, and in case of multi-electron system. So, first you see this important thing is that this spectroscopic term what is that? That I have L, that 2s plus 1 and the J value. So, that was the spectroscopic term which basically represent the state of electron or state of the atom basically. Now, earlier I told state of the electron for single electron system. Now, for multi-electron atom, so I can tell that the state of the atom at which energy this atom is having. So, this will tell this atomic state, okay. Means if 2 electrons are there, so 1 electron is at a particular state, another electron is another state. Now, resultant state will be the state of the atom, okay. So, instead of telling that that electron is at minimum energy level, instead of telling that one. So, in case of multi-electron atom or in general one, we can tell that atom is in a lowest energy state or excited state, etcetera, etcetera. Okay. So, this just language which here we just modify it for as a state of atom. Okay. So, these are basically spectroscopic term, whatever for single electron system we have used. So, that was represented the state of the electron, basically state of the atom. So, since it was single electron, so either electron or atom, this it was there was no difference. But in case of multi-electron, so now we are telling it is not, this will represent, this is basically will represent the state of the atom, okay, not state of the electron. So, although we use state of the electron in single electron system, so because that both basically meaning of both are same, but actually in general we will use this spectroscopic term, it represent the state of the atom, okay, whether it is single electron or multi-electron. So, for multi-electron, so I have to know the S. Now, S is for total spin quantum number of the multi-electrons in the atom, okay, and L is the total orbital angular momentum of all electrons. Similarly, the J value, okay, J value is the total angular momentum of this atom, okay, is summing, taking LS coupling or JJ coupling, one can find out the J value. Okay. So, I have discussed using the vector model, So, how to find out S, how to find out L and how to find out J value, okay. How to find out J value. So, basically to find out the J, this term, spectroscopic term, so I have to know the distribution of electrons in the atom, right. Atoms have different energy states, orbitals. So, So, how electrons are distributed in the atoms. Okay. So, that we have to know, and this I think all of you know. One has to, so to distribute the electrons in the atom, one has to consider the Pauli exclusion principle. Pauli exclusion principle right, Pauli exclusion principle. What it is telling? It is telling that this no electron or each electron will have distinct quantum number. Each electron have, so it is defined in different ways basically. So, N, L, Ml, Ms. Okay. So, no electron can have or can have the same quantum numbers N, L, Ml, Ms. Okay. So, each electron have distinct this number quantum number. Okay. So, they can have these three same, but this other one has to be different. Okay. So, no two electrons can have the same quantum number of these four. Okay. Or this other way, quantum state of the atoms, multi-electron atoms has to have this antisymmetric wave function. Okay. So, that way also people define. So, there are different ways this Pauli exclusion principle is explained. So, you are familiar with this one, and in quantum mechanics, in quantum mechanical language, one use this symmetric wave function, antisymmetric wave function, that way one can define. So, let us consider the whichever we are familiar. So, let us consider that one. So, considering this one, so electron can be distributed in the atoms. Okay. And how they are distributed? So, building blocks. So, periodic table is built based on this distribution of electrons in atoms. Okay. And this so any atom have different what is called this orbitals, right. So, we generally write n, say n equal to 1. So, I have written 1. So, and then L equal to 0. So, it is S. Okay. So, 1 S means n equal to 1 and L equal to 0. Okay. So, n equal to 1 and L equal to 0, S L equal to 0. Okay. So, in this case, what will be the ML value? L equal to 0, ML value 0, right. So, N1, L0, ML 0. So, MS, S equal to half, 1 electron for each 1 electron is half. So, MS can be plus half and minus half. Okay. So, here, so these three are same. So, these can be different plus half and minus half. So, 1 S2 we write 1 S2. Okay. So, in these orbitals it can have maximum 2 electrons, right. Similarly, 1 S2, if it is 1 electron, that is fine, 1 S1. If it is 2 electron, then one more it can be put here, 1 S2. But third one we cannot put here, because there is no option, right. I cannot put third one because there is no option, okay, because m equal to plus up and m equal to minus up. That is the only difference between these two electrons. The other three quantum numbers are same. So, then I have to go the higher energy level. For n equal to 2 I have to go. So, then I have to go for n equal to 2. Okay. So, why I need for n equal to 2? Because if I have more than 2 electron, so then where I will put? I will put the next higher energy level. So, that is n equal to 2, n equal to 2. Okay. So, n equal to 2, it can have L equal to 0 and 1, n equal to 2, it can have L equal to 0 and 1. So, L equal to 0 means S and L equal to 1 means P. Okay. Now, N and L, these are fixed here, n equal to 2, L equal to 0. So, for this case again ML equal to 0. Okay. So, that means here whatever I will put N 2 L 0 ML 0. So, that is fixed from here. So, now only I can vary this one plus up and minus up. So, again only in S cell it can have 2 electron, S subcell it can have 2 electron. Okay. And then for more electron, other electron, if I have, so 4 already, if I have 4 electrons, so I can accommodate them within 1 S2, 2 S2. Now, more than 4 electron, fifth one I have to put here, fine, I can put here. Sixth one where I will put, seventh one where I will put. So, let us see, in this case L equal to 1 means ML equal to 12 plus 1, how much ML value? 3, 12 plus 1 L equal to 1. So, 12 plus 1 this 3. So, ML value will be plus L to minus L, means plus 1 0 minus 1. So, it will have 3 value. Okay. It will have 3 value. So, this P again have 3 value due to ML. So, we tell Px, Py, Pz, Px, Py, Pz. Okay. Okay. So, now, so there Px it's say if it is L equal to plus 1, then Py say exactly I have to see if it is 0 and it is, I think this is maybe 0 and this is minus 1, L equal to minus 1 maybe, yes, that one has to see. Okay. It depends on angle. So, anyway, so if I consider this 3 value Px, Py, Pz, L equal to plus 1, minus 1 and 0. Okay. So, now for n equal to 2, now L equal to 1, that is also fixed, L equal to 1. Now, ML value, there are 3 value, Now, for each ML value say plus 1. So, I have 2 options, MS is plus up or minus up. Okay. So, for L equal to plus 1, this I have 2 options, I can put 2 electron. For similarly for other minus 1, I can put 2 electron, and L equal to 0, I can put 2 electron MS plus up minus up. Okay. So, here plus up minus up, but ML varies. So, that thus this 6 electron one can put here, 6 electron one can, maximum 6 electron one can put here. So, I have put already 10 electron. Now, 11th one where I will put. So, I have to go next higher energy level 3. Now, 3, n equal to 3, L equal to 0 1 2 3, 0 1 2 3, right. So, that means S, 3S, 3P, 3D, right. Similarly, 4S, 4P, 4P, 4D, 4F. So, this way one can put, and one can see that this d electron can. So s orbitals have maximum capacity. There are 2 electrons, it can contain 2 electrons, p it can contain 6 electron, and d it can contain 10 electron. One can show it because d equal to this is n equal to 3. So L equal to 0, 1, 2. So for L equal to 2 it is d. Okay. So now when d L equal to 2, so ml will be have 5 value, 12 plus 1, so 5, so plus 2 to minus 2, so 5 value, and for each it will have ms plus 1 and ms minus 1 2. So 5 into 2, so it will be 10 electron, f it can contain 14 electron. Okay. So this way one can put electrons in different orbitals. Okay. So that way in multi-electron system one can arrange electrons in the atoms. Okay. Now if this is the case, now if I consider helium atom, if I consider lithium atom, if I consider beryllium atom, okay. So I have to know that it is 2 electron, of course. Say simplest one, helium atom, it has 2 electron, helium atom it has 2 electrons. So it has 2 electron, alright. But in helium atom or any atom, these orbitals are available, 1s, 2s, 2p, 1s, 2s, 2p, 3s, 3p, 3d. So these orbitals are available. Now there is no restriction of electrons, 2 electrons to go in any of these orbitals, right. Both of the electrons, it can be here, but it may happen that one electron is here and another electron is here. That is also possible, or one electron is here and another electron is here, okay, or both electrons are here, one is here, another one is here. So all sorts of distribution of electron is possible, right. Only difference, what will be the difference? Difference will be the how we will express this difference. This difference we express basically in terms of the state of the atom. We tell the state of the atom. Okay. Now difference will be in terms of energy. And because of the different configuration of the electrons, they are staying at different orbitals, the energy of the atom will be different. Okay. So for each distribution of the electrons, there will be one state of the atom, right. So that state of the atom is expressed by this spectroscopic term, as I mentioned, right. So now if 2 electrons, if this is the configuration for helium, 2 electrons are there, but these electrons are in this way, it's distributed in this way. So here immediately I will write for first electron L1 equal to 0, okay. N is fine, N is I do not bother, N I do not bother, but one can write also N equal to, in this case N equal to 2 for both electron, okay. L1 equal to 0, L2 equal to 1, right. and then so this is L, and then S1, of course S1 equal to half, S2 equal to half, okay, fine. So I know N, L and S for this configuration. So I have to find out resultant L. Resultant L will be L1 plus L2 to L1 minus L2. So resultant L will be of course here it is 1, 0 plus 1 and 0 minus 1, we are taking magnitude. So it's 1 basically. So L will be 1, and capital S, what it will be is plus half and minus half. So S will be, resultant S will be S1 minus S2 to S1 plus S2 magnitude. So S1 minus S2 it will be 0, and S1 plus S2 it will be 1. So S can be 0 or 1. Okay. So now here I have N value, it is 2, fine. Now I have resultant total angular momentum, orbital angular momentum is 1, and total spin angular momentum is either 0 or 1. Okay. Both are possible, either 0 or 1. Now here what will be the then now what will be this spectroscopic term? So I have to find out J value. So J value will be, J value as I told this L plus S to L minus S, right. So L is 1, fine, but S either 0 or 1. So if you consider for L equal to 1 and S equal to 0, I will get J value. J value is 1, right. J value is 1. And for L equal to 1 and S equal to 1, what will be the J value? J value will be 0 to 2. So 0, 1, 2, right, because L plus S to L minus S magnitude, I will take magnitude. So L plus S, that is obviously 2. So 2, then minus 1, minus 2, minus 3 up to 0, one has to proceed. So I will get basically these 3 value, J equal to 3 value. So what will be the spectroscopic term then? So the spectroscopic term will be L equal to, all the time it is L equal to 1 means P, this is P, and for S equal to 0 means this is 1, 2S plus 1 is 1, and J value is 1. So this will be one spectroscopic term. So it will represent one state of the atom, okay, and this will tell you this spectroscopic term will be P, and S equal to 1 means 3, okay, 3, and then J value is 0. So this is 1, 0, this one will be spectroscopic term, another will be P 1, another will be 3P 2, okay. So these 3 spectroscopic term. So for this distribution of electron, so this it will have 4 states, this atom will have 4 states, and these 4 states are this, okay. and their energy. You see this here their energy, this E, it depends on J. How it depends on J? It will follow the same rule whatever we have found earlier. So, it will, so lower J value will be, lower J value will have the that J plus half, n by J plus half. So, J lower means it will be higher value that term. So, it will be more negative, yes, it will be more negative. So, this will have, this term will have the lower energy than this J value 1, then this J value 2. Okay. So, that way, so you can tell this due to this LS coupling, due to this LS coupling, the energy will be splitted, although their n value are same, okay, both electron n value are same, but their L value are different. So, obviously, L value are different, obviously their energy will be different. Now, in for same now due to this coupling, here this considering the interaction coupling, this we are seeing that it will have 4 spectral lines. Okay. It will have 4 spectral lines. So, it can have in one of these 4 states, it can have in one of these 4 states. Okay. So, in which state it is, okay, it will be take one of them. So, which state it is, so that will be basically the, because of the J value and depends of this resultant H value. So, that is decided. Okay. So, now here as I mentioned the Pauli exclusion principle. So, when this electron, in case of helium, if electron distribution is like that, so these are the 4 states, possible 4 states, it will be in one of them. Okay. Now, if really their configuration is like this 1s2, then what is the difference with the this earlier configuration? Okay. So, in this case obviously one has to find out this n equal to 1, find n equal to 1, L equal to L1 equal to 0, L2 equal to 0, right, both electrons are here. So, for each case S of course half and half. So, in this case I will get L1, this will be 0, this 0, n equal to 1. Okay. So, resultant L will be 0, resultant S will be 0 or 1, right, 0 or 1. So, now here we have to be careful. We have to be careful because whether it follows, whether it obey the Pauli exclusion principle or not, that we have to check. Earlier case we did not bother because their L value was different. N value was 2, earlier case, earlier distribution, N value was 2, right. Earlier case was here and here. So, N value was same, but L value was different. Okay. So, N, L, ML, MS. So, whether ML and MS are same or different does not matter. Already Pauli exclusion principle is satisfied because their L are different. So, we did not bother about the value of ML and MS. Okay. But in this case N equal to 1 and L equal to, also for both cases it is 0. So, N and L are same, N and L are same. So, one has to consider about ML and MS. So, one of them has to be different. Now, ML, L if L equal to 0, L equal to 0, ML is 0, ML 1 equal to 0, ML 2 equal to 0, right. So, ML value also same, right. So, MS value has to be different, MS value has to be different. Here it is telling resultant value. So, L total L equal to 0, that is fine. Now, total S, it can be 0 or 1, right. So, here I have to consider which MS are allowed. So, MS1 if it is plus of, MS2 it cannot be plus of, it has to be minus of, right. Then only it will be different, because our N is 1, L1, L2 both are 0, ML also in both cases are 0, right. MS, so MS1 if it is plus of, then in other case it has to be minus of, okay. So, that means total sum of MS, sum of is MS, MS1 and MS2, it has to be 0. In one case it is plus of, in another case it is minus of, okay. So, MS has to be 0. So, when you will get MS is total MS is 0. So, when total S will be 0, okay. Total S it can be 1 also, total S it can be 1 also, then in this case MS value will be plus 1, 0, minus 1, okay. Okay. So, this one is telling ML value will be depending on this. So, this S equal to 1, it is basically it will tell that this 2, this maximum this S MS value will get, that will be basically for parallel configuration, or both are anti-parallel configuration, okay. If one is up and one is down, so then MS value has to be 0, and corresponding if it is S equal to 0, so MS obviously it will be total MS will be 0, means individual MS if it is 1, another has to be minus 1, okay. So, in this case this will not be allowed as per Pauli's principle. So, in this case your total J will be 0, okay. So, your state L equal to 0. So, your state will be or spectroscopic term will be S, then 0 means 1 and J it is 0. So, this will be the spectroscopic term. This will be the only one possible state, of the helium, and it is basically one can see or show that this is the minimum energy. When electron is like this is the minimum energy, and this called, when this is that spectroscopic term, then this is called the ground state of the helium, okay. Now, here important things I showed you, when this is the configuration and another configuration of 2 electron this. So, here that this one we tell this non-equivalent electron, okay. We tell this non-equivalent when this is the configuration either. So, its definition is if NL of 2 electrons, if they are different, then this electron is called, they are called non-equivalent electron. if for 2 electrons, if n and l are same, then it is called equivalent electron. Okay. So, when this is the configuration, 2 electrons here, n and l, n equal to 1, l equal to 0 for both cases. So, this electron 2 electrons is called equivalent electron, and when this is the configuration, instead of this one, when this is the configuration, here n equal to 2, but l equal to 0 and 1. So, NL defined for these 2 electrons. Okay. So, they are called non-equivalent electron. Okay. So, for non-equivalent electron, it is easy to find out the spectroscopic term or state of the multi-electron atom. It is without considering the Pauli exclusion, without thinking about the violation of the Pauli exclusion principle, one can write the states easily, but for equivalent electron one has to think when you are going to find out the resultant J. So, one has to think about the resultant L and S to save, to protect the or to satisfy the Pauli exclusion principle. So, for this the two important aspect, equivalent electron and non-equivalent electron for multi-electron atom, to find out the spectroscopic term or the states. Okay. So, I will stop here. Thank you.